Before we dive more deeper, I want to define some basics of circles before we get started. This is a circle. I know it looks like an egg, but it's not perfect, but we'll say this is a circle. This is the center of our circle. There are two main things you need to remember for this unit: radius and a tangent. A radius is just from the point from the center of the circle all the way to the end and the circumference of the circle. A tangent is the line which touches the circle at one point. This is 2 points, so that's not a tangent. But say this circle has a tangent of exactly 1 point. This is a tangent because it only intersects the circle at 1 point. This is called a tangent. Okay, now we got the basics down. Let's dive into our actual unit. Okay, picture this. Okay, there are two main velocities we'll explore in this unit. One is angular velocity and the other is linear velocity. Linear velocity, we've been learning all year. Linear velocity or tangential velocity is what we've learned about so far. Tangential velocity and linear velocity are basically the same thing. Alright. Vt is the expression we use for tangential velocity throughout the unit. And our formula for that is the change in distance divided by the change in time. This is tangential velocity. How is that represented in an actual circle? Our tangential velocity is represented in an actual circle like this. This is the point. Say this is a little penny or something like that. And this is a vinyl record. Alright? This vinyl record is going in a circle. This tangential velocity, this v over t, v subscript t, is the velocity going outside of the circle. We will learn more about this, but this is technically the centrifugal force, which doesn't really exist, but we won't get into that today. And here is our angular velocity. Angular velocity looks like a W, but this is omega. It's a Greek letter. You need to know more than that. This just symbolizes the angular velocity. Okay, so what about angular velocity? What am I yapping about so much? This angular velocity represents the velocity of the actual angle. So it might be weird. Why is there a tangential velocity? What is the angular velocity? This same object experiences two velocities at the same time, and these two will have varying values. One time is it's based on how far and how much the values actually contain. Let me use equations to give you a better example. V is equal to change in position divided by change in time. Normal time is time. And since velocity, this is more like tangential velocity, right? And when we have omega, it's change in theta divided by the change in time. This is how we depict omega versus tangential velocity. And this theta in a circle is the amount of angle. This is theta. It's not look like theta. This is theta, for instance. And this, the arc length, is our change in s. This is the two different distances we use for the numerators, which give us varying results. Okay, so if velocity is equal to change in distance divided by change in time, and omega is equal to change in theta divided by change in time, how can we relate the two? Say that I have omega, and I want to get the tangential velocity. How can I get from one to another? Well, we have a formula for this as well. See, tangential velocity is also equal to change in theta divided by change in time times r. This is what tangential velocity is equal to. Change in theta divided by change in time times r. This equals tangential velocity. And since we know that change in theta divided by change in time is equal to our angular velocity, we can also say the angular velocity and radius is equal to our tangential velocity, which also means that our angular velocity is also equal to our regular velocity, our tangential velocity, divided by r. So that's the basics of r. And that's our introduction to uniform circular motion and all our circle stuff for the unit. It's just an introduction. We'll cover the basics another day. Thanks for watching, and I'll see you.